so far, just a quick recap. We learned about how data can be classified as either categorical or quantitative slash numerical. And we learned categorical data uses labels or names to identify categories of like items. And quantitative data are numerical values that indicate how much or how many. And we learned about the tabular and graphical methods commonly used to summarize both type of data. And we also learned that tabular and graphical summaries of data can be found in annual reports, newspaper articles, and everyone is exposed to these types of presentations. All of us see these type of graphics and summarized tables in our day-to-day lives, like in newspaper articles, and thus we understood why it was important to understand how they're prepared and interpreted. Okay, moving forward. Now, guys, we are entering the in some core part of statistics, which is actually the very basic one that we have learned in our 10th class, maybe 12th class, maybe again in college or graduation. But these four things, these four numerical measures, actually, uh, are four pillars behind every statistical technique. That's why I've put it as descriptive statistics too. So what we do in exploratory data analysis or in BI tools when we create dashboards, we start with some visualizations like bar charts and line graphs, line charts, pie charts, and we try to put some values on them like count, frequency, and other sorts of summarized variables. But somehow, to give an statistical angle and analytical angle to it, we try to use these kind of measures, and we all must have used it, I think, at least once in our data analytics career. So the four pillars are mean, median, mode, and range. These are very basic ones, but when understood with all the technicality and the brief, brief basics about it, these actually make the foundation of statistics. So please follow me here. So mean is I think the most important measure of location. So when I say measure of location, it means uh, it is kind of a central point of where the my data actually lies. Like for an example of that burnout example of bulb, we thought some bulbs burn out in 55 hours, some burn out in 101 hours, some in 135, some in 15 hours out of that 200 sample. But where does my actual relevant information lie? So that was the measure of location we took there, which was average, called as simple arithmetic mean. So instead of referring mean as mean, I would say we took the arithmetic mean of it, because there are other kind of means as well. You must have read that they're called geometric means. There I think one more mean is there. I don't know the name exactly. So this mean that we took there, the average, simple average, that was arithmetic mean. And sometimes we have weighted average as well with respect to the weights in one categories and other categories. So the mean provides a measure of central location for the data. So the central location for that bulb data was 76 hours. Now comes the median. So median is another measure of central location, and it may or may not be equal to median. It may or may not be equal to mean. The median is the value in the middle of the data when data is arranged in an ascending order. So let's suppose we put that bulb data in ascending order, starting from the lowest burnout hour to highest burnout hours, and the middle value that we get would be the what we call the median of it. That the most number of bulbs were focused around this median value. So let's suppose median comes out to be 82. So and it might have come around 70 hours as well, maybe. Now with odd number of observations, it's easier to find the middle term. Suppose we have five terms, then the third term is going to be the middle one. But what if we have even number of observations. Let's suppose we have the 6 terms. Then in that case, what we'll do is we'll have two medians. One would be the third term and one would be the fourth term. But we don't have a single middle value. So to calculate that median, what we will do is we will add we'll take the arithmetic mean of that third and fourth observation, and that would be called as the median. Now the mode. Mode is actually the quantifiable value, or you can say the categorical value in form of numerical measure that which how many number of hours were for that burnout bulb were maximum. Let's suppose out of 200 bulbs, we had the most common observation as let's suppose 90 hours. So we would say the 90 is the value that occurs with the greatest frequency. So it is mode is basically kind of a category. Now, why this is important? Let's suppose you are working on a machine learning model and you come to the data preprocessing. Now you encounter a column where we have the numerical values, and you encounter a column where we have the categorical values, and we have 30% of that data missing. But you do have the 70% data, which is from a reliable source, and you think using that 70% of the data, you want to impute, or you want to fill those empty missing values. Now the question comes to what kind of numerical measure you will take to do the imputation. So some would say mean imputation, some would say median imputation, some would say mode imputation. So without getting into much technicality, I would say if you have the numerical column, go with the mean imputation first. And if you think that makes your data, that if that reduces the skewness and if makes data normalized, the kind of, just do the mean imputation, plot a histogram. And if you think it is fitting into that bell curve, that normal distribution, then that mean imputation is successful. Else try with the median imputation and repeat the same steps. Sometimes when we have categories, then what we try to do is whichever category is repeating the most, what we will do is we will try to replace the missing values with that same category. Or sometimes we take two columns, like for this particular month, this value is repeating the most. So for all the missing values falling in that particular month, we will replace the missing values with the mode of that particular. So that is how these simple numerical measures are used in day-to-day life of machine learning data preprocessing. So then we have the fourth pillar of numerical measure as the range. So range is simplest measure of variability. So when I say variability, many terms arise from it. Okay, variability comes from variable. Okay, and variable is basically a column which has certain information. This column has variability, and this variability is denoted by either range or maybe variance also comes out of it. So that's why this variable, variability, variance, these all are all together. These all are related all together. So in this particular variable, suppose I want to ask what kind of range do we have for all the burnout hours. So the easy way to find the range is find the maximum value, find the lower value, and subtract that. Or maybe you can say from this to this, all data falls in there. That is how we calculate the range. But range is a very broad term because you cannot compare two data sets just basis the range. Suppose at one side you have the bulb burnout hours, and at one side you have one data set as maybe the bulb price. So what bulb price range is there? So both are on different scale. One would be in a currency scale, one would be on hour scale, and you just cannot compare the range. So that is where other terms come into play, which is called the variance. That how much variance is there in the bulb column, how much variance is there in the price of that bulb, and so on. Now, mean is not just about it. We have merits and demerits of the mean as well, and these you won't get in any statistics book very easily. These are the learnings that I learned in my post graduation, and I would try to contemplate and deliver the same in the same manner. So mean taken as a simple term is a very simple thing. Okay, let's just take a mean. What to do about it? It's just a mean. No, it's not. It's much more than that. We just learned mean is the most important measure of location, average value for a variable. It provides a measure of central location of the data. Central location of the bulk data was 76 hours, right? So all the data coming from moving forward in population, mostly it will be concentrated towards it if the data is normal. If there's a pre-assumption that data is taken in a normal distribution. Now, actually, there are, so let me, give you a background of data distribution as well. Though it's not part of this particular session because it will be too much in just one simple session. There are various data distribution. One is simple normal distribution, which says like the natural form of data. With natural form of data will be taken as a naturally occurring, the normal distribution. Sometimes there is a Poisson distribution. Let's suppose this kind of distribution is time bound sometimes, some condition bound. Then sometimes there is binomial distribution, which is choice bound, like either this or this. That's why binomial and other distributions are there as well. But for the sake of normality, for the sake of generalization in statistics, in data analytics, and in machine learning, to infer statistics about the population from the subset or I say sample, we always take norms so that we can generalize our hypothesis or analysis over the whole population. Now, let's quickly, see what are the merits and demerits of mean. So mean is very rigidly defined. Okay, it's just a simple number. You just make a sum total, divide by the number of observation, you'll get the mean. It's very rigid thing. It will not deviate much. If the data changes, mean might change, but it may not change very much. Ignoring the case for the outliers. So let me, just give you an example of how mean is used in regression. So I know you all must have read about this regression. So this is the best fit line, and this is a simple regression, linear regression. It's not multiple linear regression. There's only one x and one y, and the line equation y equal to mx plus y. Okay. So sometimes we have the actual values, and this line denotes the predicted values. Now, suppose you don't want to apply this regression. We know in that bulb burnout example, we didn't apply any regression on it, and we didn't try to find any range or try to predict the burnout hours for other manufacturing bulbs, keeping other variables keeping in mind. We just took a rigid merit out of it called mean. So this is, the mean is going to be there. By default, we will in regression by default we consider that whichever value that we are not predicting to through regression, we are just predicting it. If we are predicting it through mean, it is going to be there on. Okay. So for every bulb in population, what did we say? Yeah, every bulb coming out of production later on is going to have a burnout hour of 76 plus minus 4 hours. That's it. So that is why it is very rigidly defined. It is not very flexible. It is very easy to calculate. It's just a linear measurement, and the result is based on all observations, and it's capable of further algebraic treatment. Definitely, further algebraic treatment. When I say we can calculate a weighted average, we can, suppose we have 12 months data, we can calculate average month wise like that. And arrangement of data is not necessary. Why would it be? Because it's a simple, summation of all the observations. So order is not very much necessary. Now, of all the averages, of all the like geometric mean, okay, the another mean is harmonic mean. I couldn't remember it earlier. And then we have with geometric mean, harmonic mean, and arithmetic mean. So this mean where we summarize and divide by total number of observations called the arithmetic mean. It is least affected by fluctuations of sampling. Not even weighted average is part of it, because in weighted average, if we have higher weights to a certain category and its observations are more in the sample, the mean will fluctuate. But the arithmetic mean will will be least affected by fluctuations. So these are certain merits of it. So when you are doing the imputation, if you do, month-wise imputation in for the missing data in machine learning model, you are not, just fluctuating the mean. You are not tempering the data. You are actually pre-processing the data in its actual, trying to, bring it in its actual form. So you can definitely go with it. Now, what are the demerits of it? It's highly affected by extreme values, which are called outliers. Now we'll learn later in the session what are outliers. So outliers are the basically those values of an element of a particular variable, those observations for that particular element and variable, which don't follow the trend of the whole data and are a bit different, right? So this is the layman language of outlier, but we'll understand it in more detail. Its another demerit is it cannot be determined just by inspection or by graphical plots. No, we have to calculate it using the algebraic methods. It cannot deal with qualitative characteristics or categorical data. Suppose we saw that a cold drink example of 50 people buying cold drink. Can we calculate the mean? No, we cannot. It is for quantitative data only, and it cannot deal with the qualitative data or the categorical data. For qualitative, we'll have to go with the count or the mode. Now, in extremely asymmetrical data, that data is not in bell curve, but is either right side elongated or left side elongated, arithmetic mean is not a suitable measure because we have the outliers in the data. The data is not following a normalized manner, and that's why it's not a suitable measure. So whenever you're pre-processing a column in machine learning and you see the data is skewed, so don't just go with the arithmetic mean. Try to, uh, categorize mean month-wise and then do the imputation. Don't do the simple mean imputation, do the categorical mean imputation. And in some cases, arithmetic mean may lead to wrong conclusions if details of data are unknown. Definitely always take all statistical measures and statistics with a pinch of salt. Because sometimes it will lead to wrong conclusions. Now, next part is the median, right? Now for this GIF image, you can see, let me roll again. Arrange the data in the ascending or descending order. The middle value is going to be the median. From XS small, medium, large to XL, we have the median as the median. Okay. And the median of the data set is always unique. It cannot be, that, okay, this is also median, this is also median is going to be always unique. So if we have the even numbers, it will be, just simply the median. If the number observation is odd, then n plus 1 by 2th term. Suppose we have 5 observations, then 5 is odd, 5 plus 1 by 2 is 3. It means the third term, not 3, the third term is calculated using this formula. And suppose we have 6 terms, then it will be third term and third and half. It says third and half, but it will eventually become the fourth, and it will be arithmetic mean of third and the fourth term. The median is the value separating the higher half of a data sample or population or a probability distribution or data distribution from the lower half. So this guy here is separating the upper half from the lower half. This is called the median. Now again, the merits and demerits of median. Again, it is also rigidly defined, same as mean. It's easily understandable and easy to calculate. And sometimes just by inspection, you can, find the median from graphical manner. And unlike mean, it is not at all affected by extreme values. Why would it be, right? So this is the merit of median over mean, okay? If you have the skewed data with you guys, go with median imputation and not the mean imputation. Please remember this line carefully because it will be really helpful and it has helped me a lot. It was not there in any book. I, got to deduce it from this line that if median is not affected by extreme values or outliers, and mean is, then we, for a numerical value where we want to replace the missing values, we go with the median, not one. Now, again, we have the demerits. Data must be arranged in order before any further calculation. Definitely ordering is must here. For even number of data points, median gives rise to new observation. So, and that observation, might fluctuate. For fourth, let's suppose the third term is 300, and fourth term, let's suppose, is 500, and the median will come about 400, but it is more than the third term, it is lower than the fourth term. So sometimes it becomes a challenge with the median as well when we have the even number of observation. So sometimes you can just remove the uh, so here, for even number of records, we are actually taking the mean of the median terms, right? So again, when you go into mean, it means it is getting fluctuated. So either remove one record, make it odd, and then take. And sometimes result is not based on all observation may mislead analysts. Sometimes we do not have take this line with a pinch of salt. I just kept it for your understanding only. Result is not based on all observation, although we take all observation, but sometimes it may not be because if we don't have the complete data with us. For example, if you have a column and 70% of the values are there, 30% are missing. Now you take the median. Now that median is for that 70% values only. We cannot say with much confidence that this is going to be median for the whole column because result is not based on all observations. So with a pinch of salt. And it's not amenable to algebraic treatment. No, we don't do any algebraic treatment further on the median. We do it on the mean. There's no weighted median. There is no geometric median. There's just median. And now one demerit of median is also there, which is median. So Ankit has a question. So Ankit, I'm coming to. Now, mean has this merit that it is much less affected by samples, but it is affected by the extreme value. Now, median is opposite. It is not affected by the extreme values, but it is affected by the sampling. So be sure of your sampling. Isn't it coming to a question? Mean, median predictions also depend on skewness value. Skewness value, definitely, Ankit. See, if we have very high skewness in the data, and we have tried all the ways to normalize the data, we have converted the. So, guys, this is a machine learning question. Mean, median, imputation. So, and skewness is something to handle skewness in machine learning. We change the scale of the data, we normalize it, we take a log scale and try to normalize it. And still, if we have skewness in the data, definitely, Ankit, a mean, median, imputation depends upon the skewness value. This is what I have applied, delivering the same, what I have learned so far. So if high skewness, go with the median always because it's not affected by the extreme values. Either you can either remove the outliers, then make the data normalized, but it is not always the case. The data analytics is not a plain simple road; it's a bumpy road with even we don't know which turn we have to take at what point, right? So always try all possible measures, but it is always good to know which measure should I start. So if it is skewness, start with median. If after doing the outliers and changing the data, normalizing the data doesn't help you. Okay. Now we have mode. Okay, so mode is the value which occurs most frequently. It's plain and simple. Here we can see the 9 has the maximum number of count. So mode is 9. And data can be, unimodal or bimodal. So this data is unimodal. We have only one mode. Sometimes we have bimodal that we have two modes in the data. Okay, so when we have bimodal data, let's understand it from the point of machine learning again, because this is where we're going to apply it for data analysis. Let's say we have a column of that cold drink only. We have the highest values for Coke and Pepsi. Now, what to be done? That now we want to impute the missing values using the mode method because it's a categorical data. Which mode should we choose, right? So here, using only one column, either we can take a call with Coke or with Pepsi or with both of them. If we have the 30% missing values, we can randomly assign 15 values to Coke, 15 values to maybe Pepsi. Or if you want to take a more calculated guess, what you do is you take another column into consideration, then you find the mode according to the classes. And in that case, that bi-model data according to classes will again become unimodal, and then you do the imputation. So let's suppose we have the bi-model data for throughout the year. We have Pepsi and Coke. Now let's take let's divide the data into 12 categories month-wise, and we have the January data with us. And in January, definitely, I think the data will not be bimodal; it will be unimodal. We will get only one mode and use that mode only for imputation. So yeah, this is how we what do I say? Uh, tweak how to use this simple numerical measures and make it a powerful weapon in our data analysis in machine learning. Now, how to calculate mode? Very simple. Just arrange the data in ascending or descending order. Whichever values appear maximum or you take the count is the mode. Simple. No hard and fast. But what is important is what are the merits and demerits. Mode is easy to understand and calculate. Yeah, that's very simple. Now mode does not give rise to new observation value. No even odd problem. And it's not at all affected by extreme values. Why would it be? Right? Because we are only taking the count. If we have someone's weight as 150 for class 5 students, we have someone who has got weight as 80, who's an outlier maybe because of any medical reason or whatsoever. But the mode, if you want to calculate the mode weight, that won't be a problem. It's very useful in industries for several decisions. Okay, that's a very generalized line, very useful in industry for several decisions, because for categorical values, whatever whatever quantity occurs the most is bound to happen again. That's how we keep our subconscious thinking there. Whatever is occurring most frequently is going to occur again. So that is why I think that's there. Now, demerits of it, not based on all observation. Again, if we have the missing data issue, mode may not be the accurate value. But again, mean can also, so mean is least affected by it because mean captures the essence of all the observations and mode captures the essence of the highest occurring observation. And same goes with the median as well. That's why both median and mode share this demerit that they're not based on all observation. Now, for suppose we had 300 bulbs, I think mean would deviate to maybe 77, maybe 80, maybe 74, but it won't deviate much. But for mode and median, value can be entirely different, right? Suppose if the third term is median, it is 300. If fourth term is median, it can be 700 as well, right? So deviation and fluctuation depends upon the data itself. So that's why it's a demerit. Now, mode is not very rigidly defined in a way that when data sets have multi-modes, they are difficult to interpret and compare. So this is the case here. If we have even number of terms, we have two medians and we take arithmetic mean, but we cannot take arithmetic mean for the modes. So it is not very rigidly defined, and it gets complex. You have to divide the data into further classes and then get to know. And it's not suitable for further mathematical treatment. It is suitable only for the further categorical treatment. As I gave an example, divide the data into month category. So we cannot do any mathematical treatment on it further. We can only do a categorical or summarization kind of treatment, or maybe a subject matter treatment, experience treatment. Now, guys, we come to the relation between mean, median, and mode. Now, for a symmetric distribution, when we say symmetric, it means it's a normalized distribution. It's a distribution where most of the data falling for that data set will follow this characteristic only. Any subset, any sample of the population for a symmetric distribution will follow similar metrics only. And that is when, suppose this is a bell curve kind of shape. So this is also called a normal distribution where mean is equal to median is equal to mode. Please remember these things because whenever you go in any interview or if any client wants to ask anything, these are like core basics, the empirical rule, and this is where the central limit theorem arises. For a symmetric distribution, mean will be equal to median will be equal to mode. That means if I draw a line on the mean or median or mode, it will divide the data in two equal halves. That's why symmetry. Now, in case of skewed distribution, now skewness can be left, that is left tail elongated, or skewness can be right, the right tail elongated. The mean and median, values differ, and their magnitude also differs from each other. Now, let's suppose data is right skewed. Now, let's how it becomes right skewed. Yeah, let's suppose you have more outliers here, here, and here. Can I? Does anyone know if I can write on PPT as well? Is there any way? Can I note it? Okay. Let's see. Okay. So let's suppose we have some values here, some values here, some values here. Now, what would happen is your mean is bound to shift here, right? Because mean is a bit affected by the extreme outliers, right? Mean is affected by outliers. This is the demerit of the mean. Median may not be, but mean will be. So let's suppose you have some values here, and this distribution will become like this, and mean will, from this point, mean is moving forward. Mean has come here. Okay. Now, median might get affected as well, a little bit, not much, but a little bit. So median has also come from this point to this point. So that's why median is here. So that's why, we have this trade-off here for a right skewed data where we have the outliers on the higher side of it, on the higher side of the data. Then the mean will be more than median. Excuse me, guys, I'm getting a call again. Just give me a minute, please. Hi, everyone. So what has happened is in this trade-off of right skewness, mean has become more than median and median is more than mode. So this is a trade-off when we have the right skewness. Okay. And when we have less skewed data, that means, the more values, higher or lower values are concentrating towards the lower end or lower tail of the data, which are, pulling the mean and median towards them. Now, this is the frequency or the count. One thing that I would like to bring to your notice is mode remains the same. You see, mode is still here, still here, still here. It's on the peak only. So whatever values that are coming in here, right, the mode remains the same. In case we have similar values for the mode coming maybe negative here, maybe the data will become bimodal, but the mode is the last numerical metric that gets affected by the outliers. The first one is mean, then the median, then the mode. That's why I said if you're unable to remove outliers, go with the median imputation because mean will be most affected by the outliers. Okay. So yeah, moving forward. Now we have percentiles and quartiles. So these are also some numerical measures. I think you all must have heard of percentiles and quartiles. Like in CAT exam or GMAT, GREs, we have percentiles. So percentiles is kind of numerical measure which divides the data into equal parts. So this is the ideology behind percentile and quartiles. So percentiles basically, if we have 100%, it will divide the data in 99 percentiles, and if we have quartiles, it will divide the data into group of 25 percentiles, means called as quartiles. So we have 3 quartiles and 99 percentiles. So if I say quartile 1, that means 25% of the population I'm referring. When I say quartile 2, it means I'm talking about 50% of the population, and 50% of population is also denoted by median. We learned, right? So median is also called as second quartile. And then we have the quartile 3, which says 75% of the data, which denotes the 75% of the data. We don't have quartile 4 because it will say 100% of the data. So that's not a distinction we are creating, right? Similarly, for percentile, if we have 10 percentile, means 10% of the population falls in this category. Suppose someone has got 95% in CAT, percentile in CAT. That means 95% of the population falls below this candidate. Okay, so that's how the ranks are calculated. Then they do the binning, and then maybe they calculate the rank. Okay, they don't calculate the rank where they got the percentile. Okay, now for merits, easy to understand and calculate. We have the predefined categories. If I'm saying quartile 3 is at 100 for this particular data, then I would say 75% of the values in this data are below 100, are less than or equal to 100. And it is less affected by extreme values. Why would they be? Because it is a simple recategorization of data. We are not calculating or measuring anything. So this is how the lower quartile and the upper quartile. But why it is important? It is important to detect outliers in data, right? Outliers are the data which deviate the data from its originality and uh, make noise in the data, create I would say make our task difficult to calculate the generalized statistic. Okay, what are the demerits? So, not based on all observations, not suitable for further mathematical treatment. We cannot do any further mathematical treatment. Not based on all observations. So, why did I put this line? Just a second. Okay, please ignore this one. I'll remove this one. I'm not even remember why did I put this one here. I think it got copied. So this is not the right line. These are based on all observations mainly. No, not suitable for further mathematical treatment. Definitely, if you have already recategorized in 25 percentiles or single percentiles, we won't do any mathematical treatment on it. The result is very much affected by sampling fluctuations. Definitely, if suppose one sample we took was symmetrical or normal, one sample we took was not skewed right, and that means there's some problem in the sampling is and our sampling is not accurate. Definitely, these values are going to change. So that's why they got affected by the sampling fluctuations. Now, one more thing that the fourth pillar of numerical measures we read was range, mean, median, mode, and range. So in simplest term, it's the difference between the largest and the smallest values. That is one way of putting it. It's simplest measure of variability. But there is one advanced version of range called as interquartile range, which is the difference of the values falling on the third quartile and the first quartile. So as I said, first quartile holds 25% of the values, second quartile holds 25% of the values, and the third quartile holds another 25%. So third quartile means 75% of the values. So the IQR is Q3 minus Q1, means from this to this. So I would say from 26% to 75th%, or from 25th% to 75th% of the data is called the IQR. Why this interquartile range is very important? Because it helps us detect the outliers. So whenever we are trying to detect the outliers from statistical point of view and not subject matter point of view, uh, we have this formula. So whatever values are falling in this lower quartile will be considered not in this. There's a separate formula for that. Sorry. Just understand this is called the IQR. This is this IQR. We will find how to find outliers. Just a second. Okay. So numerical measures in this we have measure of variability. Okay. So let's see an example. Okay, and let's connect what we have learned so far to a real life example. Let me just get. Okay, yeah. Important. So far we learned about measures of location, mean, median, mode, and it is often desirable to consider measures of variability or dispersion as well. Now, why measures of dispersion or variability are also important apart from measures of location? Let's see in this example. Now, let's suppose you are a sales head of a company and you place orders from two suppliers. So we have two suppliers, Dawson Supply Incorporation and JC Clark. And you want to find, the average number of days uh, that which supplier fulfills the order in how many number of working days, and you take the average as 10 days, which is suitable for your business. If it is often more than 10 days, you are facing a operational loss, and if it's less than 10 days, then you are facing the operational loss again in terms of shelf cost or the place where you want to keep the order. Okay, so you just want the order in either in 10 plus minus 1 2 days. That's it. You cannot just accept the order in 3 days. It will cause a shelf issue. If you get the order in later than 13 days, it will cause a operational issue of production. So now, how do you now? Okay, one important measure that I have here is Dawson Supply has average number of fulfilling days is 10 days, and JC Clark also has the average number of order fulfilling as 10 days. Now my question is to all of you is, do both suppliers have same reliability? If they have the same average number of order fulfilling days, do they have? I would say no. Why? Although they are lying equally on mean, but we didn't we didn't consider the variation in this. How? So this example illustrates a situation in which the variability, like from variable to range which is variability, variable to variance. Just connect all these dots together. This example illustrates a situation in which the variability in the delivery times may be an overriding consideration in selecting a supplier. This is a real life example that suppose you're delivering a dashboard to a client and they say, okay, that it's a supply chain analytics part, and you created a dashboard and you check, okay, this is the histogram from the one distributor, this is the histogram from the second distributor, and both have the mean number of days as 10, but we can recommend you which one is better for your business. So the lower variability is shown for Dawson Supply Incorporation. So here you see we have the lower variability here, and here we have the very high variability. Sometimes JC Clark is delivering in 7 days as well, sometimes in 8 days as well, mostly in 10, but can go up to 15. And Dawson is going 9, 10, 11. Now you just cannot make this calculation based on this graph or some simple mathematical algebraic plus minus multiplication operations. Sometimes you have to apply some um, linear equation analysis. That's another part of data analysis and statistics, where we try to run certain scenarios and find where are minimal cost, minimal operational loss we are facing, and that is where we take the decision. But that's not part of this, but that is I'm just stating it because it is actually done in industries. Okay, just a second. Now we talk of variance. So the variance is measure of variability that utilizes all the data. The variance is based on difference between the value of each observation and the mean. So this is how we calculate. So this is just a formula of variance. Now, one thing is, you see there's a square here, and we so this exercise simple observation. This mu is actually the mean. We're taking a square difference and then summarizing it and dividing it with the total number of observations. So this is just a formula. But one thing to understand, that can anyone ask you, why square? So the squared units associated with variance make it difficult to obtain an intuitive understanding. We got the variance, but the square makes it difficult to obtain an intuitive understanding and interpretation of the numerical value of the variance. So that's why it is recommended that you think of variance as a measure useful in comparing the amount of variability for two or more variables or two or more suppliers in our case. In a comparison of variables, the one with the largest variance shows the most variability. So suppose you have a mutual fund that you have invested in, and volatility, which is again kind of, which is again a kind of, I would say, variance. So suppose one mutual fund has a volatility of 10% and another mutual fund has a volatility of 4%. Then whatever facts and figures you are checking for one mutual fund, which has the lower volatility, that will fall accurate and will fall in your interest. Uh, Apart from another mutual fund which has more volatility, right? So volatile is again a term itself that denotes risk. Volatile doesn't mean directly variance, but the way it is calculated, it's a subset of variance. Somehow we are measuring the risk variance, the variance in risk including in energy. So so always in a comparison of the variables or two entities, the one with the large variance shows the most variability. Now let's suppose you have risk to reward ratio. You're looking for higher returns, and you're saying that risk volatility is lower in both, which has the highest chances of getting more profit. So you will look for the higher variance in that case. So that is again the situation dependent, right? Now, further interpretation of the value of the variance, apart from this is just variance is all about. Don't get much into it. This is just variance. Now, you know, okay. So, yeah, this is one example of salary, but let's, go back to this distribution example. Now, both had the, average days as 10, but Dawson Supply had less variability or variance. JC Clark had more variation. So I'm not showing the calculations, I'm just telling the conclusion. So the company should go with the Dawson Supply because Dawson Supply, with most of the times, will fulfill the order in 9, 10, or 11 days, wherein JC Clark is giving the orders in 7 to 8 days as well, which is maybe might be profitable for the company, but you know that is not the case because the variation is very high. That means JC Clark is not a trusted supplier, but Dawson Supply is more trusted. So when I talk about trust is what that you can rely upon the service provider. Okay, if value serve says that we'll deliver this in 2 months, we'll deliver it in 2.5 months. That is okay. We deliver it in 1.5 months. That is, delightful for delightful for our client. But what if we are delivering in 4 months, 5 months, and we don't have fixed routine or fixed reliability with respect to that? So that is why in this case the sales head should place more orders to Dawson Supply compared to JC Clark. It's not that it should stop JC Clark because you should not depend on one supplier entirely. So more orders to Dawson, less orders to JC. So this is how you can present your analysis on BI dashboards as well sometimes using the simplest measures from statistics. Okay, so let's quickly go over this example. I don't want to teach you mathematics here. So it's just the monthly salary of an organization, and okay, this let's suppose this is in dollars, and we just calculate the sample mean, and then we take how much deviation is there with respect to the mean. Just a second, my laptop. Okay, so how much deviation? So one thing that I want to bring to your notice is just ignore these deviations. Just see, the sum average is always zero. Why? If this is zero, that means this data is symmetrical. This is also one indication. Then we take the squared deviations, and then we apply this formula. Now you see one question that people might ask you in interview, and it's a very common one, and I think I've always answered this one. And this question doesn't have the plain answer, but you can just try the other person make understand. Why, while calculating the population variance, we have the total number of observations, but while calculating the variance for same subset of that population, we have n minus one. Suppose we have 1,000. Suppose we have say 10 lakh rows in the population, and in sample you have taken 1,000. Here you will put 10 lakh, but here you will put 1,000 minus one. So this is how they try to put you in a tight spot. So the simple answer is to remove the effect of sampling, because our sampling may not be very accurate. That that can lead us to that can mislead us, and wrong observations can be recorded and interpreted and presented forward. So to remove the effect of sampling and to normalize the output statistic, we put this -1 to normalize the effect of sampling. This is the notation then. Now, there's another term called as standard deviation. Now, for this, monthly salary data, we got variance as $27,440. Now, this is a squared measure. Can we compare? I mean, I'm not able to interpret much out of it. This is just a number for me. To interpret the variance, we remove the one square and we take its under root, and we got this value 165. And this square root value of variance is called standard deviation. It's the positive square root of the variance. Now, one question is, if you've done all the mathematical calculation, you got the variance. Now, why are you taking the standard deviation then? What is gained by converting the variance to its corresponding standard deviation? The answer behind this is the standard deviation of this salary data is $165, right? After taking the square root. So in other words, the standard deviation is measured in the same units as original data. Salary is in dollars, deviation is in dollars. So I could say, from average salary of this company, the standard deviation is $165. That other entries that I'm considering or other data points I'm considering, they might change from a unit scale of $165 maybe. So to measure it in the same units as original data, for this reason, the standard deviation is more easily compared to the mean and other statistics that are measured in the same units. So if I want to calculate the median of the salary, the mode salary, so we can easily compare it, right? And the standard deviation and mean trade-off is taken as a quality assessment measure in Six Sigma standard industries. Now, we also I told that there's a symmetrical distribution. Now, this symmetrical distribution gives rise to mean equal to median equal to mode. Data is symmetrical. If I split it on the mean, median, or mode, 50% will lie here and 50% will lie here, right? This symmetrical distribution gives rise to two things, maybe three things. One is empirical rule, or I would say central limit theorem, or I can say normal probability distribution. So, and this is the bell curve, guys, this is the bell curve. This is the, real culprit devil behind our appraisals. So yeah, we learn it carefully. So for data having a bell-shaped normal distribution, we say, this is mean and this sigma is standard deviation. Okay. So here it says mean minus one standard deviation and mean plus one standard deviation. For a symmetrical data, we say approximate 60% of the data values will be within one standard deviation of the mean. This is the mean. If we go back one standard deviation, we go beyond one standard deviation, it will be around 68% of the data values approximately. This can be around, not exactly 68, it could be 68 point something. This is the exact figure. I am just using the word approximate. And if we go to, two standard deviations from the mean, we get around 95% of the data here. So 95% of data values will be two standard deviations of the mean. So this is the empirical rule that suggests that. So if I want to make a generalized statement on data, I can say the 95% of data will be within two standard deviations. Suppose the mean was $4,000 of salary and the sigma was 165, right? So if we subtract that, let's make it round off to 100. So 95% of the values will be within 3,800 to 4,200. Okay, within two standard deviations, plus two standard deviations and minus two. So all the salaries of the employees, of the 95% of the values of the employees, will be within this 95% range only. And almost all it's not all actually. As I said, there's no 100% in statistics. This sigma deviation is actually 99.7% actually. And guys, this is also called six sigma. Minus three sigmas here, three sigmas here, this is called the six sigma. When doing the quality assessment, um, I think Amit Kalra sir is there. He can explain more better on it. He's a Six Sigma expert. So here for quality data assessment, uh, uh, Six Sigma specialists try to put their data values, try to generalize their data into these categories, and when the data falls into these sigma boundaries, then they say, okay, we have achieved the Six Sigma optimization. Yeah, you can read more about it. And this is the empirical rule. This is also called the central limit theorem. I forgot to write it here. It's also called the central limit theorem. That 68% of the data values will be within one sigma, 95 within two sigma, and 99.7 within three sigma. Sigma is the name of the symbol which denotes the standard deviation. Now, let's come to detecting outliers. Just a second. I think there is half an hour left. And where are we? Okay, we are on schedule. Great. So outlier is an observation that is distinct from other observation. I've already explained that. Now, what are outlier detection methods that we use in machine? So one is, using the z-scores. So z-score is basically a statistical figure. One, method is there to convert each value into z-score, and all the values which are falling below -3 z-score are considered outlier from statistical point of view, and whichever are falling above +3, if some values are getting 3.4, 3.5 z-score, those will be considered as outlier. So -3 to 3 for z-score, and using quartiles IQR, as I said, which will be used. IQR was quarter 3 minus quarter 1, quartile 3 minus quartile 1. So this IQR also helps us in detecting the outliers. So the lower limit for outliers is quartile 1 minus 1.5 times of IQR, and upper limit is quarter 1 plus 1.5 times of IQR. Now, one question that anyone can ask you, or you can come in your statistical exam, or maybe an interviewer can ask you any day that what's the difference between the outliers of z-scores and IQR? Is there any difference between them? That we have other different outlier detection methods. So, guys, 99% of the times the values recorded as outliers using z-score will be same as IQR. It's just one way or another way of doing the same thing. And data outside this range could be flagged as outliers. Now, outliers also have certain categories. Is it really an outlier or it's a valid data? So let's suppose for class 5 students, one guy has weight 70 kgs and the mean weight is 60. Mean weight is what it's like. I think it should be 30 kgs maybe, or maybe more than less than that. Like 30 kg is mean, or 35 is the highest value that they have. But one guy has weight as 50 kg. So is he really the outlier? If someone records his data, definitely he's an outlier from statistical point of view. But it's the real data behind it, right? So that is a valid outlier and not an invalid outlier. How do we detect whether an outlier is valid or invalid? It's plain and simple subject matter expertise. And if you don't have the subject matter expertise, go with statistics. That's it. Okay, now and we go to the 5-point summary. We have plain and simple functions in R and Python and other BI tools as well for this 5-point summary. This 5-point summary consists of 5 points that we have our sample minimum, the minimum value. The lower quartile is quarter 1. The second quartile or the 50th percentile or median is called the second. The third quartile or 75th percentile is called the upper quartile or quartile 3 or the maximum. And this figure is called a box and whisker plot. Now, how this box and whisker plot is essential. Sometimes you can detect whether a data distribution is normal, skewed or not using the box plot itself. You don't have to calculate the skewness. You don't have to calculate, don't have to plot the data distribution on a, you don't have to plot the data distribution or plot a histogram or anything. Just following these. So right now for this data is symmetrical because mean is lying here only and median is also lying here only and mode is lying here only. Let's suppose this median is here. This median line is here, let's suppose. So what would happen in that case is the median is lesser than the mean. It means mean has deviated towards, mean has been pulled towards the higher observations. Means right skewed data. Means we have a right, we have skewness in the data and so right skewed. If median is here and mean is on lower side, that means median is more than mean. That means mean has, has been pulled away in the lower side of outliers and we have the left skewed data. So this is one intuitive way to quickly identify whether certain variables, are skewed or not quickly without, interpreting the skewness values. Now again, box and whisker plot, Q3 minus Q1 will go into interquartile, quarter 2 to the median, and that's it. So, and it's a very useful tool to detect outliers. So this value that you're seeing, some values, come up here, some values come up here. That will be whichever values are falling from this maximum to minimum will be, taken as outliers. So since we saw the formula as well, lower limit minus, what was that formula? Let's go. Yeah. So quartile 1 minus 1.5 of IQR, I think it will lie here. And quartile 3 plus 1.5 of IQR, I think that will lie here. And whatever values are beyond that will be considered outliers. Now, till so far we saw measures of location, measures of variability. There's a measure of association as well. And one example was the scatter plot, the correlation we discussed. So covariance and correlation are two terms which are measures of associations. So when I say association, it means it helps to find a linear relationship between two variables of interest. So we saw many examples, height and weight, age and blood pressure. And we also learned that this measure of association only measures that there is an association, but it does not, define cause and effect relationship like demand, supply, and whatnot. So one term is covariance, one is correlation. Now, what's the difference between that? It's also asked many times. So this is, we learned about the correlation. Covariance goes from minus infinity 0 to plus infinity. So suppose we have two values, the correlation will fall from minus 1 to 1 and covariance is from minus infinity to infinity. What is the difference between both of them? Nothing. If you have high negative covariance, that means both the values are, are have a negative association. If we have high covariance, we have positive association. But one drawback for covariance is, suppose two quantities have a covariance of 100 and two quantities have a covariance of 2000. So do we say that these have high degree of association, these have low? And which value is, considered the topmost value? Suppose in correlation we have maximum 1 and lowest also -1. But in covariance we don't have, we have infinity, and infinity is not a defined unit. It cannot be measured, right? So correlation is nothing but a standardized form of covariance. When we divide the, covariance with standard deviation of both the x and y, we get the correlation. So covariance provides absolute measure, whereas correlation provides the relative measure. Got my point? Yeah. And relative measure is more, more important than the actual measure. So again, no need to go through this slide. It's again the linear relationship, just like correlation. Just the magnitude of covariance does not really produce a fruitful meaning. We need what do I say? We need a relative measure. And correlation, it provides a measure of linear relationship or linear association between two variables. and it lies from -1 to 1. That lies from infinity to infinity. Now, guys, it's 2-7, and so far we have learned about measure of, you know, measure of location, measure of variability, and measure of association. Let's apply our knowledge and try to find, using the box plots, let's try to find the median, range, and interquartile range of each data. And so this is very basic. This is the business question of this data. Which team is more consistent? Which team has more consistent height of basketball and baseball? Okay, let's look. So to find the median, this is a box plot. For baseball, we have 70. For basketball, this line goes to 74. For range, it's simple. If it's IQR, we can subtract 78 minus 68 or 74 minus 66. Or if you want the complete simple range, we can take these values, extreme. Okay. Now, which team is more consistent? That's the idea behind it. Now, when I say consistent, that means the data is normalized, data is symmetric. And how did I just told you how to find whether data is symmetric or not. We check the median. You see, it's 4 from the lower quartile, it's 4 points away, and it's 4 points down the upper quartile. But here the deflection is much more. So it means mean would somewhat lie here and median is more. So I would say this data is that mean is on lower side. This data is left and this data is symmetrical. That means this data is more reliable than this data. This might be a wrong sample or a reason of inappropriate sampling, or it can be the natural data. It's not always the case that data is skewed. That means it's not right. No, it could be a natural cause also. But this team is more consistent because data fits in statistical framework. So what have we learned so far? We learned about the statistics, numerical measures, measures of location, variability, shape, and association. Okay, it's 2:10, and I think we have around few more slides left about probability. Uh, Probability won't be very tough part for you because I'm not going to explain you the formulas. I'm just going to tell you what probability is and how it can be utilized. It's especially for the managers people and the people who fortunately will become manager during their during after some years of tenure in the career. How do you take calculated decisions using the probability? So managers often base their decisions on an analysis of uncertainties. So we always, take our decisions based on probability. Somewhat, somewhere, we don't say that it's probability, but we are actually calculating our chances, which boils down to probability. So if you understand this part, and try to apply that to your life, you'll make much better decisions and face less consequences for your decisions because your decisions will be all calculated. Now, some examples of probability. What are the chances that sales will decrease? What are the chances that the stock that I purchased price will increase or decrease? What is the likelihood? Likelihood is another another term used for probability. So what is the likelihood a new assembly method will increase productivity? What is the likelihood this course that I'm doing right now will help me in my job? What is how likely is it that this project will be finished on time? This is the most crucial part for the manager. What is the chance that the new investment will be profitable? Now, on a quick recap, probability is a numerical measure of likelihood of an event. So it goes from 0 to 100 or 0 to 1 on a decimal scale and 0 to 100% on a percentage scale. And sample space is the set of all experimental outcomes that what all is all possible. Now, suppose we toss a coin. What would be the sample space? I mean to say, what would be the possible outcomes? If I toss a coin, it could be a head or tail on an observational record basis. I'm not saying that the coin is going to stand in the middle. That's not going to happen. Okay. So from theoretical point of view, What are the chances that are in your interest and are going to happen? Toss a coin, head or tail. Select a pair for part for inspection. Part will be defective, non-defective. You conduct a sales call, it will be purchase or no purchase. You buy a stock, it will be profitable or not profitable. Sometimes it can remain on the same price, but that's very highly unlikely. You roll a die, it could be 1 to 6. You play a football game, you win, you lose, or you tie. So for a stock as well, it could be, it could be a profit, no profit, no loss. Profit, loss, and no gain. Yeah, that would be that. So let's quickly understand, probability by example, and this will solve a lot of things for us. Um, just a second, I'm just referring my notes back to give you any brief about it. Okay, yeah. So this is experimental outcome for a project. A manager is trying to evaluate how much time it will, months it will take to complete this project. From time to time, we have to give this approach document and how much time will be taken. We define ETA in weeks, business days, months, and so on. So we can, to make a calculated decision, we can follow this method. Suppose we have two parts, design and development. Design will at least take 2 months, 2 months, 2 months. Design will take at least 2 months, or it can take 3 months, or it can take 4 months. And construction can, and the development can take from 6 to 7 to 8 months. So we have listed all the outcomes, right? And we make a simple handwritten tree. Simple, that's it. For 2 months, there are 3 possibilities. In step two, development will take either 6, 7, or 8. Or for 3 months, it could be 6, 7, 8. For 4, it again 6, 7, or 8. So we have got the all the combination, and we've got the all the possible total project completion time. That would be 8 months, 9 months, 10 months, 9 months, 10 months, 11, 10, 11, 12. Now, okay. So if I want to say what is the probability that our boss AVP maybe somebody asked us, what is the probability we can complete it in 10 months? We can simply find, okay, out of one these 10 recorded observations, 10 has number 3, so 3 by 10. There are 30% chances that the project will be completed in 10 months. And for 9, it would be like 2 counts, so 20% chances. For 11, it would be 20% chances. For 12, so say if our boss asks, can we face any delay? Yeah, definitely. For 4 months and 8 months, 12 months will not be acceptable, or 11th may not be acceptable, then we can say, yeah, 1, 2, 3, 30% chances that we'll miss the deadline of 10 months and we can shoot up. So this is about it. So this is a plain simple probability, guys. There's no condition in it.
So Sachin,
So,
how is it 30% chances for 10 months? This
no,
is
no.
Varun.
Yeah, hi, Varun. So it's like 3 counts for 10 divided by 10 occurrences. Let's say, for example, for 10, we have
But I
1 count.
can see the occurrences is 9, I guess.
Oh, okay. I read it 10. So sorry. So that total sample space is 9 counts, and for 10 we have around 3 counts. So 3 by 9 is 33% chances that project will be completed in 10 months. Thank you. Thank you for correcting me. I read it 10. Okay. Now this was plain simple probability. Now this probability realm gets really difficult when we introduce some conditions on some conditions like, what if one developer goes on leave for 3 months? What if two developer goes on leave for 15 days, one by one? What if we introduce one more developer? So this is how, conditional probability comes into play. And it's a really complex part. And since we have only 15 minutes left, and I'm just going to, tell you very, from very, we'll only touch the base on it. Let's, just understand this part. This is the last part very carefully from the example perspective. So conditional probability gives rise to Bayes theorem. Bayes theorem is a theorem which states that suppose we have some prior probabilities and we introduce new information or condition in it, and we then apply the Bayes theorem, the probabilities will change. Probability is bound, the change is bound to happen after introduction of new information. So just let's take this example and move forward. This will help us understand Bayes' theorem in a much better way than the formula in other. Suppose you have supplier one and percentage good parts is 98%. That's the figure from last 5 year data. And percentage bad parts received from that supplier is 2%. And supplier two has 95% and good percentage for the good parts and 5% for the bad parts. Now, the business objective your client has come up with this. Give him the information that the part is bad. Given the part is bad, what is the probability that it came from supplier one, and what is the probability it came from supplier two? Okay. Now, your clients ask you like, I'm getting bad parts. What is the probability that it will come from first supplier? And similarly, what is the probability it will come from supplier? So just to find out, the given the information, the part is bad. This is the our problem statement. Now, please note this part. Bayes' theorem is applicable when the events for which we want to compute posterior or new updated probabilities are mutually exclusive. So when we say mutually exclusive, that means we have received a part. It is going to be either good part or bad part. It cannot be both, right? So either it's going to be mutually exclusive good or it's going to be exclusively bad. So that's why mutually exclusive. They cannot occur all together. Now, for the solution, let's go forward. So now this term denotes here, given the part is from, let's suppose A1 denotes supplier 1 and A2 denotes supplier 2. Okay. Now we have one more information here, guys. 65% of the parts purchased are from supplier 1 and remaining 35% we purchase from supplier 2. So this is also a fact figure we'll take into consideration, right? So that is how the conditional probability changes. Now, at present, how it looks like is, please understand this term. P means probability. G by A1, it means probability the part is good when it is coming from supplier. Okay, so the part is coming from supplier 1 and is good. So we already have this number 98, or we can say 98%, or we can say 0.98 or 98%. Similarly, for bad coming from supplier 1, 0.02. Similarly, 95% and 5%. Okay. Moving forward, we have got four figures. Now, there is a multiplication rule as well, that each of the experimental outcomes is intersection of two events. Why? That part is good and part is coming from supplier. So there are two probabilities into play, right? So that's why it's an intersection of two events, and we want to find what are the chances that these two events are going to occur together. That probability part is bad and it came from supplier 1, right? So we have to calculate individual probabilities and do some formula kind of thing. And this formula application is simply Bayes' theorem. Okay. So let's suppose part is from supplier 1, part can be good or part can be bad. So part can be good is 98%, we just saw. Part good can be, bad could be 2%. Similarly, 95% and 5% for supplier 2. We had one more information we saw. 65% from supplier 1, 35% from supplier 2. So we put this information here as well. Now, probability of outcome that part is good and is from supplier 1. Now, guys, please understand my words. It is not the problem statement. It is something else. That part is bad or part is good. It's what is the probability it came from supplier 1. So it is a co-occurrence of events that we received a good part and it is from supplier 1. So we got this, we just multiply these two values and we got these values. But are we going to use this? No, that doesn't solve our purpose, because our purpose is to give the information part is bad. Now, one of you could say part is good and part is from supplier 1. Why not we subtract it from 1 and we got 36 something, and that could be our final value? No, that is not the problem statement here. This event is different from this event which is there in the problem statement. In the problem statement, we have already got it that the part is going to be bad. Find the probability, it is from supplier 1. And it is saying supplier 1 and good. What is the probability of these two events occurring together? Okay, so just forget this part for now, and I think it's plain and simple and clear these values. Let's move on to the application. So Bayes theorem, this is the formula behind it. Definitely now we're going to utilize Bayes theorem. We'll use the formula as well. Now it says the part is already bad. What is the probability it came from supplier one, right? And part is bad, it came from supplier two. So this is the formula. I'll share the PPT. You can understand the formula, and let's calculate. After applying this formula using the Bayes theorem, we get the part is bad and it's coming from supplier one is 43%, and part is bad. It is coming from supplier two is 57%. So the final conclusion is in this application, we started with a probability of 65% that we are ordering 65% parts from supplier one. But one part was selected at random and was bad. So this information given that part is bad, the probability that part is from supplier one drops to 42%. Although 65% parts are from supplier one, but given the part is bad, it will be 42% of the times. But and given the part is bad and what is chances of it is from supplier two, it is 57%. And guys, why this is relevant? Because it has better than 50-50 chance. Okay, you say we have two suppliers and we're getting a part. What are the chances it will be faulty? You can say 50-50. No, it won't be 50-50. Given all the facts and figure, the actual figure would be 42% and so this was, the concept of conditional probability or Bayes theorem and the simple theorem and multiplication rule of events. So since it's already 2:30, and as I said in the starting, statistics is not something we can cover in 3 hours. So next steps were to, if we do have a follow-up session, if you want, or if we tend to have, the next part for you, if even if you don't have the session, just go out and read about what is normal distribution, why it is required. I've already answered it. How to check whether a data follows a normal distribution or not. It will tell you about statistical test. I've told you about some box plot method and skewness method. What are z-test, t-test, and what is hypothesis building and sample test. So okay, so now I conclude my session. Any question, feedback? Yeah, I'm open to it.